Greetings, and this presentation is called Game Theory. What is it good for? Now, in an earlier presentation, we surveyed Hamilton's universe, and we said Hamilton's universe has four corners. We talked about spite being mutually destructive. We said that cooperation is very attractive but challenging to achieve. And we said that altruism was an even bigger problem to understand. And game theory helps us to understand why that's the case. It gives us really precise analytical tools for thinking these problems through. So in Hamilton's altruism model that we started out going over, we had two players, blue and orange, and we said in an altruistic act, blue would benefit orange. So that green arrow is a benefit, and orange turns green. And as a result of that, blue was harmed. So blue turns red to show the harm. And that was Hamilton's initial model of what an altruistic act was. Now, game theory makes a difference to that, and the difference is this. It lets us model social interaction or outcomes that depend on the actions of more than one player. So what if the outcomes in that altruistic encounter depended not simply on what A chose to do, but also depended on what B chose to do? The prisoner's dilemma, it's a simple mathematical model, and it's been used to analyze cooperation for over 50 years. But game theory is notationally challenged, and this is a quote from Herb Gintis, who's an evolutionary economist. I've also found in teaching this that the story of the prisoner's dilemma causes more confusion than clarity, so we're going to just drop the story altogether. And we're going to take a card game approach. We're going to have two players, player A and player B, who again are blue and orange. And each player has two choices. They can choose play or they can choose hold. And those are their only options. So imagine them, they each have just one card. They can either lay it down or they can hold it. Because there's two players, it's a 2-by-2 player game, and they each have two options. It means there's four outcomes possible. If both players play their card, both get 5 points. If player A plays and player B holds, then A loses all his points and B gets 8 points. But if player B plays and player A holds, then player B, she gets 0 points, whereas A gets 8. And lastly, if they both hold and don't play their card, they both get 1 point. So this is a very simple scenario. So let's play a hand here to see how this works. The first hand, A plays and B plays. This means they both get 5 points for that hand. Let's play another hand. This time, player B plays and player A holds. That means A gets 8 points and B gets 0. Let's try another hand. This time, they both hold. This means both get 1 point. Let's give it one more hand. This time, player A plays and player B holds. And this means A gets 0 points and B gets 8. So we all know we struggle a bit when we start learning games to master the rules, but after we played a few hands, we can start to see the logic of it. And after we played a few more, we might start analyzing things and thinking about, what's the best way I could play this game? So let's look at it from the perspective of player A, the blue player. What should player A do? Well, one thing player A can do is play, and if player B also plays, player A will get 5 points. However, player A could also hold, and if player B played, player A would get 8 points. And since 8 points is a greater number than 5, in the scenario where player B might play, player A should always hold. Well, what if player A plays and player B holds? Well, then A will get 0 points. On the other hand, if player A holds and player B holds, A will get 1 point. So what's the outcome here? Well, player A should always hold because 1 point is greater than 0. So from the perspective of player A, she should always hold her card because she's going to get a better score than she would if she plays whatever strategy player B plays. So after A has thought this through, A is just going to sit there and hold her card in her hand and refuse to play. Well, what should the orange player do, player B? Let's look at it from that perspective. If player B plays and player A plays, B will get 5 points. However, if player B holds and player A plays, B will get 8 points. So considering this, B should hold because 8 points is greater than 5. Here's another option. Player B plays, but player A holds, and in that instance, B gets no points. But if B holds and A holds, B will at least get 1 point, and this means that B should hold because 0 is less than 1. So from the perspective of player B should always hold. So once these two players have played a while and figured this out, we can imagine them, they're just both going to sit there with their card in their hand and refuse to play, and each will get 1 point each turn of the game. If they both hold, they earn just 1 point per round. However, if they were to both play, they would each earn 5 points per round. So let's move from these two players, let's have pairs of players. And we know we have blue and orange, and they've decided that they're just going to hold their card every round. And then we have these other two players, purple and brown. And somehow purple and brown have decided they're going to both play their card every hand. So in the first round to play, the player blue and player orange, they each earn 1 point. But purple and brown, they each earn 5 points. And then in the second round, blue and orange earn an additional point. But purple and brown now they're up to 10 points. So if we compare them, right, and if we imagine these points are offspring, then clearly the pair of players who's decided to both play their card are going to accumulate increasingly more offspring than the players who've decided to just hold their card. And what this tells us is if this was a reproductive strategy in a population, the players who learned to play would produce more offspring. So let's put this into a context of Hamilton's universe again. So here we go. We have these two corners. On the one hand, if both play, they both get 5 points. On the other, if they both hold, they both get 1 point. And in terms of Hamilton's universe, we could call the corner where they both play cooperation. And there it's 5 plus 5 points that are given at each round, or 10. And we could call the corner where they both hold the spiteful corner. Down here they each get 1 point, or 2 points per round. Now we said, right, that according to the individual self-interest of player B, it would appear that player B should always hold. And if this is the case, player B is going to push their play towards the spiteful corner. And the same thing holds for player A. If player A is playing a selfish game, then player A is similarly going to push things towards the spiteful corner. And it appears that if they both play their own self-interest selfishly, they're going to continually end up in the spiteful corner. And our question is, how do we get out of that spiteful corner and up into the cooperative corner? So what has to happen to move from spite to cooperation, from both getting 1 point to both getting 5 points. And what are the obstacles to that? Well, for this to happen, both players have to risk being an altruist. So let's look at this again. Let's say that player B decides to play, and player B has to do this if they're going to hit that cooperative corner. So what's the risk in this? Well, the risk is that player B will choose to play and cooperate, and player A in turn will be selfish and hold. And in that, if that happens, B will become an altruist, and A will be the selfish winner. A will take all the offspring, all the points, and B will get none. And the same thing holds from A's perspective. In order to get to the cooperative corner, player A must risk playing, but in doing that, player A is risking altruism, because if player B plays hold, then A turns into the altruist, giving all of her offspring to the other player, and player B is the selfish winner. So to get to cooperation rather than spite, these two players have to somehow decide that it's better off for them to cooperate than to play their selfish hand. So to get to cooperation, both must risk being turned into an altruist. They both have to take a risk on altruism, and if they do that simultaneously, they'll hit cooperation. So the risk is there for both of them, and this is the heart of the problem. To get to the cooperation, both must forego selfishness and risk being turned into an altruist. And this means that they must effectively reciprocate altruistic acts between them. Now, if the game repeats over and over, and this is called an iterated prisoner's dilemma, then there's interest of both of them is to cooperate. If they play just one hand, the interest of each player is to hold their card. But if they're going to play over and over and they're competing with other pairs, the interest of the players is to both play. And this means that any pair of players who might evolve this cooperative strategy, who might choose cooperation over selfish behavior, would quickly outperform those who simply play a selfish strategy. Their offspring would proliferate, and pretty soon, if this cooperative strategy was genetic, there'd be cooperators running around everywhere, and selfish players would diminish in number. Now, you might be saying at this point, well, what about the prisoners? Isn't this the prisoner's dilemma? And the answer is we don't need the prisoners. We don't need the story about them. What's called a prisoner's dilemma is any game, any two-player game like this, where the numerical points are counted such that the selfish play from an individual perspective gets a higher return than the cooperative play, which gets a higher return than spite, which gets a higher return than altruism. But what makes a prisoner's dilemma is the structure of the payoffs. It really doesn't matter what numbers I use, and it doesn't matter what story we tell. It's simply that the benefit to selfish play has to be higher than the benefit to cooperative play viewed from an individual perspective, as long as the payoffs are arranged in that manner. All right, thank you for listening.